Hello, welcome to this new edition of our video lecture series on random processes. And we have seen that autocorrelation function is an important tool in analyzing random processes. Today we are going to look at a similarly important tool, another important tool for analyzing random processes, which is called power spectral density. For ordinary signals, we know there are two domains in which we can do analysis of signals. One is a time domain and the other is a frequency domain. And there is this mathematical device called Fourier transform, which allows us to go back and forth between this time domain representation and frequency domain representation of functions. There is an equivalent tool for random processes also, which is now what we are going to study. But before that, let us briefly look at what the ordinary Fourier transform does for ordinary signals. Let us consider a deterministic signal. This is a deterministic signal. There is nothing random. A single signal which is deterministic. And then the Fourier transform of that signal is ST is defined this way. We multiply the signal by e raised to minus I omega t and then integrate from minus infinity to infinity. When you do the integration with respect to time and when you substitute minus infinity and infinity for the limits, this integral will finally be cleared of the t variable, the time variable, and this will be a function of omega. This omega represents the frequency of this signal. So this is called a Fourier transform. And then we can recover the original function st by doing an inverse Fourier transform. That is, if you have the Fourier transform, you multiply it by e raised to plus I omega t. Here it was minus I omega t, but in the inverse Fourier transform it is plus I omega t. And then you integrate with respect to omega, the frequencies. And then there is a factor 1 by 2 pi here. This factor is there in the, when we do the integration in the frequency domain, you have an additional 1 by 2 pi factor. And when you integrate with respect to omega, you will recover the original function st. So let us look at these two. These are called a Fourier transform pair. This gives you the Fourier transform, this gives you the inverse Fourier transform. There are a number of conventions which is used. In the Fourier transform, we use e raised to minus I omega t, whereas in the inverse Fourier transform, we use e raised to plus I omega t. Now, this is purely a convention. You could equally well use e raised to plus I omega t here, then you will have to use e raised to minus I omega t. But this is a convention which is. Similarly, this factor 1 by 2 pi, you can write it here or you can write it here. Or you can split this 1 by 2 pi into two factors, 1 by root of 2 pi in both places. It is all valid, but this is the common convention to write e raised to plus I omega t here and to multiply by 1 by 2 pi when you are in the frequency domain. So these two constitute what is called a Fourier transform pair. So st is the signal in the time domain. When you do the Fourier transform, you get a new function which is the frequency domain representation of that function of that signal, and this gives you the frequency information about that signal. For example, let us look at these two transforms. This is the time domain function e raised to minus mod t. And if you apply the Fourier transform, this is the Fourier transform you are getting, 2 by 1 plus omega square. And this is a representation in the time domain. This is a representation in the frequency domain. And what does the frequency domain information tell you are the frequencies which are present in the original. Frequencies means frequencies of the sinusoids which are contained in this signal. So this signal, that means that this signal ft contains a continuum of an uncountable collection of sinusoids, each differing from the other in their frequencies. These are the frequencies. And if you look at the height of the graph here, gives you the strength of the frequency. So that means that the lower frequencies here are stronger. The lower frequency components are stronger, and as the value of the frequency increases, the strength of that frequency, the contribution by that frequency becomes smaller and smaller. So the lower frequencies are dominant. Now, how we are going to do this for a random process? A random process situation is more complicated because a random process consists of usually an infinite collection of signals, and most of these signals need not have Fourier transform also. Even Fourier transform may not exist for most of these signals. So how we are going to handle this situation? And the idea is, instead of the signal, instead of the individual signals, we take the autocorrelation function of the random process. And it turns out that instead of taking the Fourier transform of the individual signals contained in a random process, if you take the Fourier transform of the autocorrelation function, you will get something in the frequency domain which happens to be a very important quantity for the random process. This is called the power spectral density. We will see that this power spectral density has a lot of desirable qualities with which we can do analysis of the random process in the frequency domain. And whenever you have a Fourier transform, you also have an inverse Fourier transform. And the inverse Fourier transform of power spectral density gives you the autocorrelation function back. So this is a Fourier transform pair. So that means the autocorrelation function and power spectral density are Fourier transform pairs. And now what does that expression mean? This is the Fourier transform. The power spectral density is denoted by Sx omega. So you multiply the Fourier means the autocorrelation by e raised to minus I omega tau, and then integrate from minus infinity to infinity with respect to tau, you get autocorrelation. Now e raised to minus I omega tau is cos omega tau plus I sin omega tau. So you can split this into two real integrals. Actually, this is a representation of the sum of these two real integrals. This is Rx tau into cos omega t. This is Rx tau into sin omega t. So this is the real part, and this is the imaginary part. So the Fourier transform is a complex number. It's a complex function. There is a real part and an imaginary part. But let us see whether we can further simplify this expression. We already know, we have seen the properties of autocorrelation function. We have seen that Rx tau, the autocorrelation function, is an even function. And because Rx tau is an even function, you can simplify this expression drastically. So Rx tau is even, cos omega t is known to be an even function in tau. So the product of these two even functions is again an even function. And if an even function is integrated from minus infinity to infinity, it can be written as 2 times the integral from 0 to infinity of this function. This is a property of integrals. So the first expression here can be simplified into this integral of, instead of integrating from minus infinity to infinity, you need only to integrate from 0 to infinity and multiply it by 2. This follows, this is a consequence of the symmetry of this product, which is even. And similarly, there is another property that this Rx tau is even, sin omega tau is an odd function. The product of an even and an odd function is odd. When an odd function is integrated from minus infinity to infinity, or between any a symmetric interval minus a to a, it is going to be 0. So that means that because our autocorrelation function is an even function, the Fourier transform simplifies. The imaginary part of the Fourier transform becomes 0, and you are left with only the real part. So that means that although in general the Fourier transform is a complex quantity, in this special case of the autocorrelation function of a WSS process, it becomes a real quantity. The imaginary part becomes 0. So that means that the power spectral density of a real process is actually a real quantity. Not only that, we can simplify the integral into this form. Instead of integrating from minus infinity to infinity and using e raised to minus omega tau, you can simply multiply it from multiply the autocorrelation with cos omega tau and then integrate from 0 to infinity and multiply by 2. That will give you the power spectral density. So this is a special simplification which is possible only for a wide sense stationary process for which the autocorrelation is an even function. Okay, now let us look at some of the properties of the power spectral density. One property we have already seen, it is real. We will see that it is also an even function and it is non-negative. The first part we have already seen. And in this expression, if you replace omega by minus omega, then what happens? This cos omega tau becomes minus cos omega tau. But cos is an even function, so cos minus omega tau is the same as cos omega tau. So you get back to the original expression, which is Sx omega. So Sx minus omega is Sx omega, which means that Sx is an even function. So the power spectral density is real, it is also even. And there is a third property, which is that the function, this Sx omega, is always non-negative. We will not prove it. Anyway, power spectral density is a function which satisfies these three conditions. It is real, it is even, and it is non-negative. Not only that, it can be proved that any real, even, and non-negative function can be the power spectral density of some random process, which is a strong result which basically characterizes the power spectral density. And as a byproduct of this result, that the power spectral density is real and even, we have another result which simplifies the expression for the inverse transform. The inverse transform recovers the autocorrelation function given the power spectrum, and it is given as integral minus infinity to infinity Sx omega e raised to I omega tau d omega Now you can write this as the sum of a real and an imaginary part like this. Now since we have just now proved that Sx omega is real and evens, and this becomes 2 times the sum of this, the 2 times this integral, and Sx omega is even, this is odd, the product is odd. So the imaginary part, this integral will become 0. So we are only left with the real part, which is 2 times this integral from 0 to infinity. So it becomes 2 times 1 by 2 pi will become 1 by pi integral 0 to infinity Sx omega cos omega tau d omega. So Rx tau can be expressed this way also without the imaginary part. Now we will move on to another topic, which is another concept, which is Dirac delta function. And this Dirac delta function is a device which engineers use to represent impulse force or sudden variations in voltage or current strength across an electrical network. If there is a spike in the voltage or current strength in a network, then they use a delta function to represent that. And the delta function is desired to have these properties. Means this delta function has a very high value at one point and 0 value elsewhere. So it is a spike at that point, t is equal to a. It is infinity, which means it is a very large value at that point and 0 value elsewhere. And the second important property is that the integral of that function over the entire time domain from minus infinity to infinity should be 1. And if you multiply the delta function by another function ft and then integrate, then this delta function acts like it selects the value of the function at that point. So basically it is not easy, it is not possible for an ordinary function to satisfy these two conditions, that it has a very high value at one point and 0 value elsewhere. At the same time the integral is 1, because this kind of a function, which is a point function, which has a value is non-zero only at one point, usually will have an integral which is 0. So it is not possible for it to have an integral 1. So how to construct such a function? For that we use another limiting mechanism to define the Dirac delta function. So this is how we define a Dirac delta. This is a pulse whose width which extends from a minus epsilon by 2 to a plus epsilon by 2. So it is a small interval of length epsilon, and in that small interval this has value 1 by epsilon and 0 elsewhere. Everywhere else its value is 0. And the pulse looks like this. It extends from minus infinity to minus epsilon by 2 to plus epsilon by 2. It has a height which is 1 by epsilon. So the width is epsilon, the height is 1 by epsilon. So the area is actually 1. The area of this pulse, this graph, under this graph is 1. And in this, if we change epsilon, if we make epsilon still smaller, what would happen is something like this. If you make epsilon smaller, its width decreases, it becomes thinner and thinner, but the height increases. So if we go on decreasing epsilon, we get a series of pulses whose width becomes smaller and smaller and whose height becomes larger and larger. But at any moment the area under the pulse is 1, because the area is 1 by epsilon into width epsilon, which remains 1. and the limit of this pulse as epsilon tends to 0. That is what we call delta function. So this delta function defined in this way has the property that it has a very high value at one single point A but 0 value elsewhere. So we arrive at this function, this kind of a function satisfying this condition and at the same time this condition, and you can prove that the delta function defined as above will also satisfy this condition, the third condition. So this is called the delta function. In fact, there is no real function which can satisfy this. This is a mathematically shaky idea to have a function which satisfies these two ideas, and this can only be justified by using some other concepts such as distributions, which is beyond the scope of our lecture. But for the time being, we will look at the delta function as an operator which satisfies conditions 2 and 3 and which also has this property. If you treat it as an operator having these properties, then it is a very good model for impulse for sudden voltage variations in electrical circuits, etc. Now, these are some standard Fourier transform pairs which are also valid pairs of autocorrelation function and power spectral density. And some of these results includes delta function and also some results which can only be expressed in terms of delta functions. And with the idea of a delta function, we can also define what is meant by a white noise. A white noise is a zero mean random process with a flat power spectrum. Flat power spectrum means the power spectral density is a constant. If the power spectral density is a constant, if power spectral density is 1, we know that the corresponding autocorrelation function, which is the Fourier transform, will be the delta function at the origin. So if the power spectral density is constant alpha, then the autocorrelation will be a delta function at the origin multiplied by alpha. So you can define a white noise as a random process having zero mean and having a flat spectrum, or having autocorrelation which is a delta function. So autocorrelation is a delta function means all samples are uncorrelated. Let us consider this random process for which the autocorrelation is e raised to minus alpha mod tau, where alpha is positive. Let us find the power spectral density. Now this is rather straightforward, but we will have to use this result. The integral of e raised to ax into cos bx has this expression. This is something that we have already seen in our course on integrals, indefinite integrals. So we will use that result. Using that result, it is now straightforward to calculate the power spectral density. This is the expression for power spectral density, which is as the autocorrelation of, as the Fourier transform of autocorrelation. But we have already seen that we can simplify it into this form without the imaginary part. 2 times integral 0 to infinity of this. Now this is an integral from Rx tau is e raised to minus alpha tau. We substitute that, and then this integral we can calculate using this result, and it turns out that the result is this T alpha by alpha square plus omega square. So this is a result worth remembering, that if the autocorrelation is e raised to minus alpha mod tau, then the power spectral density is 2 alpha by alpha square plus omega square. I said this is worth remembering because to do it the other way around will be very difficult. Suppose we are given uh, the power spectral density which has this form, then if we try to find the inverse Fourier transform by actual computation, it is going to be a little difficult. But because this is a Fourier transform pair, if we know one side of the Fourier transform, we already know the other side. So one side is easier to prove, that the Fourier transform is e raised to minus alpha tau is 2 alpha by alpha square. So automatically the inverse Fourier transform of 2 alpha by alpha square plus omega square is going to be this, e raised to minus alpha tau. But to prove that would be a little difficult, so we will definitely remember this as a result whenever we want to find the inverse Fourier transform, whenever we want to find the autocorrelation of some random process whose power spectral density has this form, we will use this result instead of computing the inverse Fourier transform, which is difficult, and write the result in this form. And these are the figures. This is the autocorrelation function, e raised to minus alpha mod tau. This is the power spectral density. These graphs are drawn for alpha is equal to 1. Now let us look at another random process having autocorrelation function, the triangular function. Then the power spectral density, okay, it is very straightforward to calculate. We have this formula which reduces to this formula without the imaginary part. Then Rx tau, actually Rx tau is non-zero only between minus 1 and 1, but because this integral is 0 to infinity, we need only take the part of this graph from 0 to infinity only, and in that the graph is non-zero only from 0 to 1, elsewhere it is 0, and from 0 to 1 it is 1 minus mod tau, which becomes 1 minus tau. So it is 1 minus tau cos omega 2. You simplify, you will get this, and this you know is the sinc function, so we can easily draw its graph. Sin theta by theta is the sinc function. So this is the graph. So if the autocorrelation is the triangular function, then the power spectral density is going to be the square of the sinc function, which will have a graph like this. Now let us look at another example. This is the band limited white noise. That is a flat spectrum from minus B to B in this frequency band, from minus B to B, 0 elsewhere. Again, this is very easy to prove. Here we are given the power spectral density. We want to calculate the autocorrelation function, so we will use the inverse Fourier transform. But we have seen that even the inverse Fourier transform can also be simplified without the imaginary part, using only the cos omega tau in the integral. And you can simplify the expression, you will get something like this. Again, there is a sinc function here. The autocorrelation is a sinc function. And once you have the autocorrelation, you can calculate the power also by letting tau tends to 0 in Rx tau. So this is the power. You can also calculate the power by integrating the power spectral density. You will get the same result. This is the graph. This is the band limited Y noise. If the power spectrum is like this, then the autocorrelation is going to be the sinc function. The autocorrelation can have both positive and negative values, but not the other way around. The power spectral density is always non-negative, but the autocorrelation can have. You cannot interchange these two figures. Means the power spectrum cannot have this shape, the single function shape, because the power spectral density is always non-negative. But this has both positive and negative values. Now, this is a continuation of the last example. We want to know whether this is a valid autocorrelation. So the autocorrelation is something like a rectangle is something like a pulse between minus t and 0 otherwise. Now this seems to be an okay function if you look at the properties of autocorrelation. This has a maximum value at the origin, this is even, and so. So this looks like it is a valid autocorrelation, but we can be only sure if we take the power spectral density. I mean, if we take not the power spectral density, we don't know whether it is an autocorrelation, so we cannot call the Fourier transform a power spectral density. We will simply take the Fourier transform of this. And we have seen previously that if we take the Fourier transform of this, it is going to be a single function. This. And this function, it is this function. This function takes both positive and negative values. This Fourier transform. So this Fourier transform cannot be a valid power spectral density because the power spectral density is known to be non-negative. Since this is not a valid power spectral density, this cannot be a valid autocorrelation function. These are few exercises based on the problems and the discussions that we have had. Given the power given the autocorrelation function, you have to calculate the power spectral density. And here it is a reverse process. Given the autocorrelation function, you calculate the power spectral density. I mean, given the power spectral density, you calculate the autocorrelation function. And some similar problems. These problems I assign to you as a homework. Thank you.